Let's look at what these equilibrium constants mean. So I can have a certain reaction and it has a certain equilibrium constant, and notice that this is an extremely large number. And this is calculated by taking the products, their concentrations divided by the reactants. And if I have more than one reactant, I would multiply. So that's how I find that number, the concentration of the products divided by the concentration of the reactants. In order for Kc to be so large, this numerator must be much larger than the denominator. Therefore, the equilibrium concentration of the COCl2, it must be greater than that of those reactants. And so this tells us that the products are favored, or I'll end up with more products. So if you have a K that is bigger than 1, that means that you have more products. If you have a K, an equilibrium constant, that is less than 1, then that means you have more reactants. So the equilibrium will lie closer to having more reactants than it will more products. So you'll only form just a few products. And this slide sums up just what the previous one did. Again, if your equilibrium constant is bigger than 1, then you have more products. If it's less than 1, then you have more reactants when you achieve equilibrium. Here's another picture of this. Again, if you have more products than reactants, you're going to have a number that's bigger than 1. And if you have more reactants than products, mathematically it works out that your KEQ is going to be less than 1. And what happens if it is 1? Then that just means it's equal. And that's a pretty rare situation where you have equal products as reactants. Let's do an example where we have some data that we can plug into our equilibrium constant expression. So it says find Kc for this reaction. Those are both gases. And then I'm going to go down here and I'm just going to pick one experiment. It doesn't really matter which one you pick. Maybe I'll pick this bottom one. And there's lots of values here to look at. I have some initial concentrations and I have some concentrations at equilibrium. When you're writing an equilibrium constant expression, you want to only use those concentrations that are at equilibrium. So it's only these right here that I need. So I'm going to put my NO number, and then remember I have a formula there. It is squared, so don't forget to do that. And there's my N2O4 value, and let me just do the math. And I get a value of 0.213. So this tells me that I have more reactants at equilibrium. A lot of times we can use the equilibrium arrows to show this. So I would have something that looks like this. Just a little bit this way, but have a larger arrow going this way. So that would just show that the equilibrium lies for more reactants than it does products. In other words, it's easier to do the reverse reaction because I end up getting more reactants. Let's look at a multi-step reactions, and there's several rules. So in a multi-step reaction, that means that I have one elementary reaction and then a second one, and I can add them up to do an overall reaction. Well, each of these steps can have an equilibrium constant expressions. And if I add the equations, you take and multiply the equilibrium constants. So that's a little bit different than you might expect. So with these equilibrium constants, you end up getting really, really large numbers or really, really small numbers as a possibility. So again, find your equilibrium constant for each step. To find the total, you're going to multiply each of the mechanism steps. Rule number 2, if an equilibrium reaction is written in the opposite direction, the new equilibrium constant value is the inverse, so 1 over the equilibrium constant. So you would do this if you're adding two equations to get a total equation and you need to reverse one. So or maybe you just want to look at it a different way. So let's say I'm going to reverse this reaction. So I can reverse it. So my products are now my reactants are now products. I would have a new Kc value because you always put the products on top and the reactants on the bottom. And this is going to equal the inverse of this one that we had. And when I do that math, I end up with 216 as my value of K. So now it's favoring the products. So at equilibrium, I'll have more products than reactants. A third rule is if you multiply an equation by a power, then the K is raised to that power. So you don't So if you double the equation, you don't double the k, you instead square the k. So for example, here I have this reaction. It's a 2-to-1 ratio and I have my Kc is 216. What would happen if I multiplied through by 2? So this would give me a 4-to-2 ratio. So my Kc, I would end up wanting to square it. So that would give me about 46,656. If I did 6 figs, it would be 46,700. So again, if you double an equation, then the new equilibrium constant would be the square of that. So just like if I multiply by 2, I would want to square it. If I divide by 2 or multiply by half, then I would take the square root. In my first example, it's a 2-to-1 ratio. If I were instead to have a 1-to-1/2 ratio, this would be 1 mole to 1/2 mole, I would take that 216 and take the square root of that. I would get about 15 for my K. So still favoring the product side, but less strongly. So let's look at an example where we would use these rules, where we would multiply through by a certain coefficient or divide or reverse a reaction. We always have a target equation. So our target equation is there at the top. Calculate value of the equilibrium constant for this equation. So I have some ammonia, some oxygen, nitrogen, and water. And here's my two given equations. So what I want to do is I want to take these two equations and make it so that when I add it up, I get my target equation. So let's look at the first equation and try to see if I can find anything that matches. And I see that there's an oxygen and there's also a water. My target equation has 3 moles of oxygen and 6 moles of water. So for this equation, I am going to take and multiply through by 3. Everything gets multiplied through by 3. So this becomes a 6, this becomes a 3, and this becomes a 6. And then I take this and I am going to raise it to the power of 3. And then let's look at the next one and see if we can match anything up. I see that I have a nitrogen here, but the nitrogen in the target equation is on the other side. So I'm going to reverse this equation. And remember, when you reverse the equation, then you're going to take the inverse of the K. So I rewrote that, so I'm just going to cross out this equation because I don't need it anymore. All right, let's just double check that we have everything as we should. So we now have our NH3 on the reactant side, but I do see that there's a 4 there. So that means I'm going to multiply this one by 2. I still need to work with it. This becomes 4, put a 2 in front here, and this becomes a 6. This one becomes squared because I multiplied through by 2. All right, let's add everything up and see if it equals our target equation. I'm just going to try to match the target equation. So I have 4NH3. I can bring that down. I have a 3O2 I can bring down. And then I do have 6 hydrogens, but I see that I have 6 hydrogens here. So I know that that's probably a catalyst, perhaps. So it's at the beginning, at the end. So I can eliminate that. So that's going to be on my reactant side. Let's look on the product side. So on the product side, I have 2 and 2. And I have 6 waters. So it looks like everything's accounted for. So I need to multiply these Kc values. So I'm going to have 1.7 times 10 to the 27. That's a huge number. It looks like I'm going to make it even larger. And I'm going to multiply it by 1 over 1.5 times 10 to the 2, and that's squared. So I get 4.91 times 10 to the 81. So this is very strongly favoring the products so far. And I think multiplying this number is not going to really affect it that much. It's still going to favor the products. And this ends up being 4.4 times 10 to the negative. So my final answer is 2.18 times 10 to the 77. That's pretty ginormous. This is going to strongly favor the products when it's written this way. So go ahead and stop the video and answer these questions. So a review of our equilibrium constant expressions if we are adding up some elementary steps. The answer to number 1, what happens if the reaction is flipped or reverse? Well, then you would have your K be the inverse. What happens if the reaction is multiplied by 3? Then you would have your K to the third. And what happens if the reaction is multiplied by 1/2? You would have your K to the 1/2, which is the same thing as square rooting it. Number 4, in a multiple step reaction, to find the equilibrium constant for the overall reaction, you would blank each of the individual step equilibrium constants. You would multiply them. How did you do?